In the microphone. Can you guys hear me? Yes. Okay. Okay, so it's time to get started. So let's get started. So the audience is somewhat smaller, but let's see what happens later. So this is what we are gonna do today. So first of all, as always, so please make sure you indicate where you are for today in this Google Sheet. So there's a sheet for today. So please do it until the exercise time begins. And hopefully I'm going to finish this last memory management part today. So hopefully within an hour or so. And from something like 11:25, you're going to work on this exercise. So either PL05, or if you are done, just go ahead and continue working on PL06. Okay. And so one apology. I have to go to the faculty meeting that happens in Kashiwa campus. So after my part is done, I'm gonna run to the Kashiwa campus. So this happens right after the lunch break. So I cannot be here until the end of this period. So anyway, so from sometime around 11:30, the time is basically for your exercise. So I'm gonna disappear around that time. So sorry about that. So I'm gonna designate some of you here as the host of the Zoom meeting, so that the breakout room still remains. Okay, so shall we get started? So since the last week, I started talking about this Rust management. And the last week, I was actually solely focused on this box type. But just as a recap, so this is the basic idea behind the Rust memory management. So you have something called, so one and only one owning pointer that basically determines the lifetime of the data itself. So when this is how the Rust basically manages the underlying memory. But of course, you can have other pointers pointing to it. But they are called borrowing references, borrowing pointers over borrowing references. So one thing that is crucial for this to be safe is that borrowing pointer should never be dereferenced after this owning pointer is gone, the data itself is gone. So it is not safe to dereference these borrowing pointers after the owning pointer is gone. So this is the basic idea. And the last week, the main topic was this one, so owning pointer. And to maintain, there's only one owning pointer. The Rust has a somewhat surprising semantics for the assignment. So when you make performance assignment like this, the pointer moves from the point variable to the other one. So you do something like B equal A, the pointer that was originally in this A variable will essentially disappear. So you can no longer use this data structure through this variable. So A.x is invalid. So that's how the Rust maintains the single owning pointer rule. Okay. And I was talking about some other situations and some exceptions. And yes, some details about the distinction between box T and T itself, but these are not vitally important here. So this is the new part. So that there's only one owning pointer. So there's actually a huge implication of this rule. So the single owning pointer rule. So one of them is that with only owning pointers. So forget about the borrowing pointers for now. I haven't talked about pointers T or a box T. You can make, for example, a tree of T like this. But you can never make a general graph of T, either a cyclic or cyclic, only with owning pointers. Because, so this is not a tree. So you have some pointers pointing to the same node, or there's a cycle like this. So if you want to make a data structure that looks like this, you need to have at least one node pointed to by two or more owning pointers, right? So this is a huge implication, right? So you cannot make a graph solely based on box T. Of course, you can make a graph either using borrowing pointers I'm going to get into later, but you cannot make a graph only with a box T or T itself. So never waste time trying to do that, right? And so there's another way we often use to make a graph is you simply make a vector of all nodes, right? So this vector has all nodes, and you represent edges by a pair of indexes, right? So rather than having the direct pointers to nodes, so this is somewhat more straightforward way to represent a graph in Rust, or in some other language too, actually. So you don't necessarily have to have a direct pointers between nodes to represent a graph. So there's a way around this, but this implication is huge. And another implication is that so with only owning pointers, no two names in the same scope ever refer to the same object. So in shortest term, this is something something we can call no aliasing. So as a concrete example, so let's say you have a function that takes two box T pointers. It never happens that A and B point to the same data, because there's only one owning pointer to a single data structure. So this is basically a good news for the compiler trying to optimize memory references through these pointers. And it is actually a useful property for the programmer too in some cases. Some cases, of course, it's sort of inconvenient. But in other cases, it is a useful property to avoid mistakes. So oftentimes, when the programmer is given two pointers, the pointers through two different variables, well, the programmer tends to implicitly assume these two different things, and you somehow forget about taking care of a special case or corner case in which these two data structures are actually the same. So this is a couple of important implications for of this single owning pointer loop. So then the next, before we move on, so let me show you a simple example in which this actually matters. So let's say you have a structure, and this is another structure that has two of S's. So both are basically owning pointers. And you can write a program that looks like this. So you have, you create a T, and each of whose fields point to S, right? And you can reference T to get both S0 and S1 and do whatever. So this program naturally compiles. So nothing particularly surprising about this program. But for example, let's say you reference this S0 twice. So instead of both S0 and S1 once for each, then the compiler complains by saying, so value moved here. And the compiler is complaining about the second reference to this S0. So this is how you understand why this is an error. So because this S0 is an owning pointer, this assignment is essentially moving the pointer out of this S0. Right, so S0 now refers to the data you created here, right? So if you follow the single owning pointer rule, then T.S0 can no longer refer to the same data structure. So it is now this S0 variable that refers to the data structure. So you cannot reference this again. Right. So actually the compiler was sort of smart enough to figure out this is safe, but this is not safe. So in a way that the compiler is keeping track of which variable has already been referenced in this context. So at this point, S0, so T.S0 is already invalid. In a way, it's already gone, but S1 hasn't. So that the compiler is sort of smart enough to figure that out. And around the same token, for example, you cannot put this in a loop like this. So, oops, no. Syntax is always confusing. So you so statically, you have only one statement that refers to T.S0, but this statement is obviously executed twice. So this is another invalid program that is not allowed by Rust. So this time, no, I didn't make another error. Sorry. So I always forgot what is the right syntax in each of these languages. So this time, okay, so it was complaining. So sorry about this one. So remove this one. And okay, so again, it was a warning. So I'm just trying to execute this assignment twice by the loop, but it complains by saying the value has already moved in previous iterations, right? So you cannot reference T dot S0 twice. And even stronger restrictions apply when this is an array rather than the struct. For example, you have an array of 2 elements. Well, semantically, it's almost exactly like making another struct, right? But if you say something like this, then the compiler even complains about this. Or even if you if you imagine what actually happens at runtime, you never violated the single owning pointer rule, right? So you actually reference this element only once, and you do not reference any other element or the same element anymore in this program. But yet, the last compiler complains. Essentially, in the case of arrays, the difference is that from the compiler's perspective, it's much more difficult to track which element has already been out, which element still remain. So essentially, as soon as you take an element out of the array, the compiler complains. So it's as restrictive as this. So obviously you need to have something else, which is borrowing pointer. So this is a simple illustrations of borrower's rule, so-called borrower's rule. So borrower's rule is again, basically a borrowing pointer cannot be dereferenced after its owning pointer, and thus the data structure itself is gone. So this is what the Rust tries to maintain. So let's say you have a program like this. So you have a borrowing pointer at the top level of this foo function, and you have an inner block. You have another reference variable. So both are not pointing to any data structure at this point. And now you allocate the data structure itself, and A becomes an owning pointer. So let's say whether this is safe, it is safe to assign a reference to this data structure to this B variable. Well, it appears to be safe because, okay, so you declare this A variable, owning pointer, in this scope, which means that if you do not do anything particular after this, this data structure is going to be reclaimed at the end of this inner block. So this is where this data structure is going to be released. But B is also released. B is also gone at the end of this inner block. So this is not a so-called dangling pointer. So this data structure lives at least as long as the pointer pointing to it. So this is sort of not the dangling pointer. It's a safe pointer. But consider whether this is safe. So you assign this reference to the other variable C, which is declared outside this inner block, which means that the C may be dereferenced somewhere around here after this inner block is done. So this is a dangling pointer. So potentially this may be a dangling pointer. Well, strictly speaking, this becomes a dangling pointer after this inner block is over. So this is potentially a dangerous pointer assignment. So basically, this pointer variable lives longer than the data structure pointed to by this variable. So this is potentially a dangerous, something called dangling difference. So like I said, a data structure, so this data structure is going to disappear here because A is going out of scope at this point. So this makes C a dangling pointer. So if you reference C, the X field of C or any other field for that matter, it's dereferencing a dangling pointer. So this is one of the things that has to be prevented from happening. And this is exactly what the Lastre is trying to prevent. So let me show you it actually happens. So this is exactly what I have showing in the slide. So exactly the same thing. And when you try to build this program, so it complains by saying we go ref A. So borrowed value does not live long enough. So it's sort of confusing. So let me make it simpler. So by doing something like this, you it is more obvious that you are making a dangling pointer. So it says borrowed value does not live long enough. So basically saying this value does not live as long as this variable C. So this is what this error message is complaining about. But the somewhat more remarkable is, so the Rust compiler can keep track of how much this B is going to live. Essentially keeping track of this assignment. So basically, what it is complaining about is the same thing. So borrowed value mut A does not live long enough because borrow later are used here. So one more thing that is somewhat orthogonal to what I have been talking about. But so remember that there is another kind of borrowing reference, which is something called the mutable borrowing reference. So in terms of the syntax, it was something written like ref mut t. This is a type expression. So it actually has an additional restriction. So the restriction is even stronger on this ref mut t. That which is that you cannot use the originating the original owning pointer, or you cannot derive other borrowing pointers from a mutable borrowing reference, while a mutable borrowing reference is active in scope. So for what I mean by that active. So let's consider this example. So you take you make a mutable reference to this data structure created here. And let's suppose you are going to use this mutable borrowing pointer here. So without technically precise definition, we say this mutable borrowing pointer is active from this line 3 up to this line 7. So the rule says that you cannot use either the originating pointer A in this case, or derive other borrowing pointers from this M. So, for example, you cannot use you cannot write something like a dot x because a mutable borrowing pointer is active on this line. Also, you cannot derive another borrowing pointer from the originating or owning pointer, just like this. Or this. So those things are all errors. So this is slightly different things from what I have been talking about in the last slide. But basically, again, the Rust tries to maintain something called the no aliasing rule for this mutable borrowing reference too. So basically, so a mutable borrowing reference enjoys the same property as the original, well, not exactly the same, but similar property with the original no aliasing rule that applies to owning pointer. So it is that like an owning pointer, a mutable reference also enjoys the no aliasing property. And if you follow the rule stated in the last slide, it is actually even stronger. So it cannot alias with other borrowing references. So just as an illustrating example, let's consider a hypothetical function that takes many forms of pointers to t. So one mutable borrowing pointer, two ordinary borrowing pointers, and owning pointer and another owning pointer, which is in of type box t. So many forms of pointers to t. And following the rule stated in the last slide, it is guaranteed that a p mutable pointer cannot be an alias of any of others. So you can assume, or that the compiler can assume that p and all other variables never point to the same data structure. So the only possible aliasing between these variables is that Q and R, so ordinary borrowing pointers, may be pointing to the same data structure. No, it's not the only possible aliases. So Q, for example, may be an alias of A or B. So these things can happen. But A and B cannot be an alias of each other. So there are so many things. The Rust compiler, it can safely assume something that compilers of other languages cannot. But this is a subtle point specifically about mutable borrowing references. And so that the following discussions are sort of orthogonal to these special rules that apply to mutable references. So the following discussions are focused on the memory management, so lifetime management issues, and largely apply both to immutable and mutable references almost equally. So I'm going to move on. So if you have any question at this point. Okay. So yeah, like I say, these are two different sorts of pointers, box T or left T. So you might be naturally wondering, yeah, how, so when you have to use which one, right? So like I said, well, so it's difficult to describe This is the situation where you have to use box T, and this is the situation where you have to use mu T in a very short sentences. But generally speaking, so box T is the pointer that determines the lifetime of the data structure you are pointing to, right? So basically, you typically use box T to link data structure together. So when you want to make a huge tree data structure, pointers between nodes are normally made by box T. Unless you have some other data structure that maintain all these box T pointers. And you typically use ref T to work on existing data structures without affecting the lifetime of the data itself. So without any allocation or deallocation. So for this reason, many functions that take data structures, so that functions working on existing trees take as input ref T rather than box T. So if you write a function that takes box T, then actually that function determines the lifetime of the data structure pointed to by this pointer, right? So if you take an argument, a parameter of box T, and if you do not do anything particular on this, then the data structure will be gone when the function returns. Well, unless you take this box T somewhere else and put it somewhere else, right? So this is what happens if you take a variable, take a parameter of box T and do not do anything particular on it, so that it lives longer than the function itself. So for that reasons, if you just want to write a function that works on existing data structures and do not do anything particularly to deallocate data structure, you typically take ref T rather than box T. So a few more details about borrow checking rules and how the Rust maintains no dangling pointers. How Rust guarantees dangling pointers are not dereferenced after the lifetime of the data structure itself is over. So one technical remark about borrower's rule is that, so it's not the creation of a dangling pointer itself that is not allowed, but the dereferencing of dangling pointer. I actually made that clear from the beginning, but there's a slight difference between the two, right? So it's not necessarily that as soon as you make a dangling pointer, a potentially dangling pointer, that program is rejected. So that the program is rejected when you make a dangling pointer and dereference it. So as a matter of fact, I slightly modified the code I have shown before in such a way that you do not dereference this C pointer after this inner block is over. So it is still true that you have made a dangling pointer, right? But this program actually does not cause an error. So let me slightly modify this the program that originally caused an error to something like this. Well, it's useless. So you might wonder what is this C variable made for, but just for the purpose of illustration. So if you do not dereference this C, then Well, it issues a warning like, okay, you are not using C. Is anything wrong about this? But it doesn't signal any error, right? So this indicates that well, you can actually have a dangling pointer as long as you are not dereferencing it. So that's a subtle difference between what you might have thought is going on and what is actually going on. So here's a somewhat more precise statement or a precise understanding about how this borrowing rule actually works. So for each borrowing reference, lefty or left muti type, so Rust compiler determines the lifetime of data it points to. So let's call it a different lifetime because I'm going to use, so we're going to use this notion so many times. So different lifetime of a borrowing pointer is the lifetime of data it points to. So please remember this terminology, different lifetime. So Rust compiler determines different lifetime of each borrowing reference as part of its static type. So it tries to determine its static type, and the static type of each reference type includes the lifetime of the data it points to. So the lifetime of its reference. So this is basically how the Rust compiler is trying to reason about this program. So you have a reference and you have another reference. And at this point, the Rust compiler hasn't yet determined their different lifetimes. And when you do an assignment between borrowing pointers like P equal Q, where the type of P and Q are references, the Rust compiler basically equates, so think they are the same, their reference lifetimes are the same. So the Rust compiler basically assumes different lifetimes of both pointers are the same. So more specifically, okay, so let's say, so you have, like before, you have two assignments, V equal ref A and C equal B. So the way the Rust compiler reason about this program is that looking at this assignment, the Rust compiler assumes that B's different lifetime is A's lifetime. A is the owning pointer. So its lifetime, its different lifetime is exactly this where the scope of A is ended, which is here. So when A goes out of scope, then the life of the data it points to will be over, right? So basically A's different lifetime is here, right? So let's call it alpha. So a hypothetical point in time when this data structure is gone. And by looking at this B equal ref A, the compiler figures out, okay, so the different lifetime of this B is alpha. So this is the different lifetime of this B variable. And the compiler sees another assignment, C equal B. Again, the compiler thinks C's different lifetime should be equal to B's different lifetime. So C's different lifetime becomes alpha 2, right? And the compiler sees this dereferencing expression C dot X. but alpha, so the compiler thinks alpha ends here. So alpha is here. So C dot, so this expression appears outside alpha. So this is why the compiler signals an error. So the third rule that is going on is that the difference in a borrowing pointer P, or P dot X, is allowed only within the P's reference lifetime. So this is basically how the Rust figures out whether the difference is safe or not. So assign reference lifetime to each borrowing reference. And for each dereferencing expression, it determines whether this expression appears inside or outside its lifetime. Is it clear? So if you have any question, please ask. Okay, so this is somewhat more formal, no, not exactly formal, but a somewhat more formal description of how this borrowing rule works. So there's something more you have to know when you actually program with these borrowing references. So programs using borrowing references or references sometimes have to help compilers track their different lifetimes. So it's not necessarily that you simply write ordinary programs and the compiler figures out everything else. So sometimes you have to annotate your program. So this is the sort of intended lifetime of difference of these borrowing references. Well, especially this has to be done when you are using functions or data structures. So functions called from unknown places and function calls to unknown functions and data structures. So to this end, the programmer sometimes has to annotate reference types with their different lifetimes, so sort of intended lifetimes of their reference. So let me show you what I exactly mean by that. So basic problem. So forget about what I have just said in the last slide. So just look at this program. So let's imagine you have a function, something called the p points q, that takes two borrowing pointers, one to p and the other to q. And you simply put the reference to q to one of the field of the other one. So p dot x equal q. So now after this function is returned, you have two data structures, P and Q, and P pointing to Q, right? So how to check if this function is safe? Without knowing all its callers and function calls passing references. So you can, so I hope you can easily understand that this is not safe unconditionally. Right, so because basically we like to prevent dangling pointers being made, right? Well, more precisely, dangling pointers to be dereferenced, but approximately speaking, you don't want to make dangling pointers. But if referent life, so in this particular case, if T lives longer than Q, then at some point, P dot X becomes a dangling pointer, right? So obviously you cannot allow this function without any other knowledge. or any restriction on the way this function could be called, right? So this is a very specific example in which this might go wrong, right? So you have a variable C that lives longer than this B variable, which is declared in this inner block. And if you call this function F, sorry, P points to Q in this way, then there's going to be a reference from C to B, right? But C lives longer than B. So if you have a differentiating expression like C dot X dot Y, after this inner block is done, it's going to be dereferencing dangling pointers, right? So this at least shouldn't be allowed. But how can the Rust compiler can do it without knowing the definition of F? Yeah, this is the setting we have to work with. In general, you do not know what is happening inside a function, right? So the language has to allow unknown function to be called, only knowing their types, not the body of the function itself. So something else to be known about this function, other than just taking two references, right? In order for the compiler to know if this is safe or not. And a similar thing happens for functions that return references. So a similar but a slightly different problem is that how to check the validity of functions that look like this, that returns a reference. So it is a function that returns a reference to P. And you somehow make a reference to P, for whatever it is, and returns P. And you return this function to obtain a reference to P, and later dereference this pointer. Well, how to know this is safe? So you have to be able to figure out whether the function, the return value of this function lives at least up to this point. Well, something you can easily imagine is difficult to know without looking inside the function, which is not generally possible. So you have to assume that some functions are unknown from the Color's compilation unit. So something else has to be known about this function, in addition to bare minimum fact that it is returning reference to P. So something has to be known about the different lifetime of P, right? And yet another example is references in data structures. So let's say you have, so you obtain a reference from another data structure A pointed to by A. So you obtain a reference to P and dereference it here. So how to know the different lifetime of this P is longer than at least this line 4. So the different lifetime covers this line 5. So you have to know something beyond that A dot P is just a reference to P. So something has to be known about its different lifetime, right? So the list goes on. So the other possibilities go on. So what about functions taking data structures containing references and returning another containing references? So you can think of arbitrarily complex functions involving differences, right? So there must be something that tell the compiler the different lifetimes of all these differences, right? So here comes the notion of something called the lifetime parameter. So something you have to know when you are programming in Rust to any serious degree. So to address the problems I have been talking about in length, Rust borrowing different types, either ref t or ref mu t, carry something called lifetime parameter, essentially representing their different lifetimes. So how long the data structure it points to lives. So this is the syntax that specifies lifetime parameter for differences. So ref tick a t, which represents reference to t whose lifetime is tick a. So the syntax is sort of pathological. But basically, you just add this tick A or tick B or whatever, just right after this left symbol. So rather than just a left T, you have left tick A T or left tick A mu T. Pathological. But basically, this is a type that represents, for example, in this case of left tick AT, references to T whose lifetime is tick A. So this data structure is going to live until tick A. So for what is tick A, which is very confusing, but well, let's think of it as a hypothetical timing point that represents the time at which this data structure is going to die. So every reference carries a lifetime parameter, even if they do not appear in the program surface. So, well, actually, the thing is, these lifetime parameters can be omitted at some cases. So in those cases, you can just write ref t without this tick A. But in other times, you have to explicitly say the lifetime parameter is tick A, the lifetime parameter is tick B or something like that. But basically, you have to write them wherever they are needed. But roughly speaking, you must write them explicitly in function parameters. So when you are writing a function that takes differences, or a function that returns differences and struct or enum fields. So you have a structure or enum and that have differences in one of its fields. And oftentimes you can omit them for local variables. So this is roughly what you typically experiences when you program with references. So this is how you actually attach lifetime parameters to functions. So this program does not compile. So you are writing a function that takes 3 references to integers and return a reference to an integer. So the Rust compiler complains expected name lifetime parameter. Yeah, this is where you start to become very confused when you try to master Rust programming without looking in, without without solid understanding about what the lifetime parameters are. And White goes on to say, okay, so I'm suggesting you write something like this. You simply add these tick A in front of each of these variable names, which still doesn't make sense, does it? But you have to understand the concept rather than this superficial fixes suggested by the compiler. But so without explaining, so why does compiler complains like this, and why the fix suggested by the compiler is the way you can fix it. Let me talk about why do we need such an annotation. What is the fundamental reason why you cannot live without it? So the reason is that without any annotation, you cannot know whether this is safe without knowing the definition of this function foo. So let me get to it. So you have three variables of different lifetimes. So C lives up to this point, B lives up to this point, A lives up to this point, right? And you have expression R dot X, which is assigned by this function call. And let's hypothetically assume that you know that foo is going to return one of them, one of A, B, or C. But still, you cannot know whether this is safe or not without knowing which of these three parameters foo is going to return, right? So if foo is going to return this left C, then clearly it's not safe, right? So you are differentiating essentially the address of, well, I shouldn't say the address, but you are trying to obtain this 7, 8, 9 after C's lifetime is over, right? So this R dot X is safe only when foo returns this one, right? So this is something you want to indicate it. You want to indicate by lifetime parameters of this foo function. So it's essentially, of course, that the compiler has to know something about this foo function, and so when so forget about this. So I guess you got what I was saying. So this is how you can actually specify lifetime parameters of functions, either parameters or return values. So you explicitly introduce what kind of lifetime parameters you want to use to specify lifetimes of these variables or return values. You can introduce any number of lifetime parameters like this. So right after function name, you have a bracket, not exactly bracket. So less than or greater than equals symbols. And you can use these parameters to specify different lifetimes of references that appear here or here. So you can use them in T0, T1, and TR. So in this particular case, one way you can specify the lifetime parameters of foo looks something like this. So you use only one lifetime variable, one lifetime parameter, and say all these references have different lifetimes of tick A, and the return value is another reference whose different lifetime is tick A. So this is one way you can attach lifetime parameters to this function. So what happens if you say something like this as the type of this foo function? The net effect is the return value is assumed by the last compiler to point to the shortest of these three. So why this is what effectively happens. So basically, the way the last compiler figures out the lifetime of a different lifetime of this return function is that, okay, so the compiler knows the lifetime of each of these three variables. So A's lifetime is up to here, right? And B's lifetime is up to here, and C's lifetime is up to here. So let's call each of them alpha, beta, and gamma, respectively. And when you call this foo function, the compiler knows, okay, the first argument has a lifetime of alpha, a different lifetime of alpha. The second one has a different lifetime of beta, and the third one gamma, right? But if you look at this foo signature of this foo, they all have the same different lifetimes. So basically, the compiler assumes that these are all the same. And because they are obviously different, the only thing the compiler can do is simply to assume that this tick A is the shortest of the three. So tick A becomes the shortest of alpha, beta, and gamma, which is gamma. So essentially, the compiler figured out that the return value, the return value's different lifetime is gamma. So the only as long as the lifetime of C. And compiler figures that this is going to be unsafe. It may be C. So what you can fix this problem if in fact foo is going to return A, not C. So A is A lives longer than C. So if the original foo function looks like this, then this should actually be safe, right? So there must be some way to tell the compiler, okay, so this should be safe. You have to reason about it, right? And the way you can allow the last compiler to figure out this is in fact safe is something like this. So this time you attach different lifetime parameters to each of these three variables. But the only thing that is significant in this particular example is that this first parameter has a different lifetime with other two variables. But just for the sake of simplicity, let's say, yeah, each of these variables has distinct lifetime parameter. And you indicate the return value different lifetime is tick A, that of the first parameter. So this is a critical part, right? So by writing this way, when the last compiler sees something like this, it is able to figure out the different lifetime of R is the same as the different lifetime of A, which is alpha here. And it can figure out that the difference is in fact safe. Right? So this is how the lifetime parameters help the compiler understand which the difference is safe and which one is not. So any question at this point? So I hope you got an idea. And I think with that, I think I have to finish my part for today, and so leave the remaining time for your exercise.